Here we have 6 new derivatives involving logs and exponentials, and we'll prove all 6 of them. But don't worry, the proofs are very short, and they're actually pretty interesting because they use the properties of logs and exponents in unique ways that allow these proofs to come out pretty nicely. Once we step through these proofs and we've justified that these are true, we can feel free to use them in all our work and exercises moving forward. So I recommend internalizing all 6 of these so you can have them on ready recall. All right, let's step through them one at a time. We start with the derivative of natural log x equals 1 over x for x greater than 0. This x greater than 0 bit just comes from the domain of natural log. So we're already limited to x greater than 0 just from that domain. So the proof of this is pretty straightforward, really. Let's just write y equals natural log of x. And then we'll take both of these sides base e. Well, the e and the natural log undo each other, so we're left with just x on that right side. So I'm going to write this as x equals e to the y. And now I will take the derivative of both sides, d by dx, d by dx. Well, the derivative of x is simply 1, so we have 1 equals, and here we're going to use the chain rule to take the derivative of e to the y with respect to x. Well, the derivative of e to the y is e to the y again times the derivative of the inside, so to speak, with the chain rule, so we'll write that as dy dx. Well, dy dx is what we're trying to solve for, so then we have dy dx equals 1 over e to the y. But remember that y is simply natural log x, so we can write this as 1 over e to the natural log x. The e and the natural log undo each other because they're inverses, so that tells us that dy dx equals 1 over x, completing the proof. Number 2 says that the derivative of the natural log absolute value of x is 1 over x again, but now we just have x not equal to 0. Well, that x not equals 0 simply again comes from the domain of the original function. The domain of natural log of absolute value of x is fine for every single number except for x equals 0, where it's undefined. Now, here we need to remember something about the definition of absolute value of x. If you recall, one way of looking at the absolute value of x is that it's simply x if x is greater than 0 already, actually greater than or equal to 0. And then if it's less than 0, we just replace x with negative x, which makes it positive if x is less than 0. So that's one way to look at absolute value. So then we'll just do a couple of cases here. So let's say case 1, x is greater than or equal to 0. If that's the case, the derivative of natural log absolute value of x, well, is simply the derivative of natural log of x, which we already know is 1 over x. So there's that first case. The other case is x is less than 0. Then we have the derivative d by dx of natural log absolute value of x is now, well, since we're in x is less than 0, we replace x with negative x. So that's d by dx of natural log of negative x. Okay, we'll hit this with the chain rule again. So we know what the derivative of u is essentially. So it's 1 over negative x times the derivative of the inside, which is the derivative of negative x, which is negative 1, which brings us back to 1 over x again. So that tells us that no matter what, x greater than 0 or x less than 0, or even x equal 0, but that's actually not in the domain, we have the derivative as 1 over x. So let's fix one thing here. This case should actually just be x greater than 0, because we can't have x equal to 0 in there. Okay, so there we go. There we have it. 1 over x no matter what. That takes care of that. Moving on to number 3. The derivative of log base b of x is 1 over the quantity x natural log b for x greater than 0. Well, same thing. The x greater than 0 just comes from the domain of log base b of x, so not much to say there. The proof of this one is fairly direct using our previous proofs that we've already done. We can use the change of base formula to convert log base b of x to essentially log base e. There's the change of base formula from somewhere in algebra or pre-calc land. So let's use the natural log version of this. So this is now the derivative d by dx. Instead of log base b, I'll write this as natural log x over natural log of b. Well, natural log of b is a constant, so I'm going to just bring 1 over natural log b out to the front of this derivative, so d by dx of natural log x, which we know is the derivative of natural log of x is 1 over x. So we have 1 over natural log b times 1 over x, which finally gives us 1 over x natural log b, which is what we were looking for. Number 4 says d by dx of log base b of absolute value of x is equal to 1 over the quantity x natural log b. And now this holds for x not equal to 0. That x not equal to 0 simply comes from the domain of log base b of x. And the proof for this is exactly the same as in number 2 where we did natural log absolute value of x. So I won't repeat it here, we'll just accept this one as proven. For the next one, for number 5, we have the derivative of b to the x is b to the x times natural log b. To prove this, we first need a fact, and it's an interesting fact about exponents and logs, and that is that any b to the x can be written as e to the natural log b to the x. Why is that? Well, e and natural log are inverses of each other, so they undo each other, leaving us simply with b to the x. So any exponential can be written that way. That's just a trick. So moving on to the proof of this here, the proof, we use that fact. So we say the derivative d by dx of b to the x. Well, that can be written as the derivative d by dx of e to the natural log b to the x. And then we'll use our properties of logarithms here to bring this x down to the front, which gives us the derivative d by dx e to the x natural log b. Well, we know what the derivative of e to the u is, so let's use the chain rule on this to compute this derivative. So that's simply e to the x natural log b. You just rewrite what you have, and then times you take the derivative of the inside. Well, the derivative of x natural log b is simply natural log b. But now let's take this first expression again. Remember, this whole thing is simply b to the x, right? Because we move this x back up into the exponent, the e and the natural log undo each other, and we're left with b to the x again, times natural log b, which completes the proof. Number 6 is the derivative of x to the p equals p x to the p minus 1 for any p in the real numbers. And you may be saying, we already have done the power rule, we've been using it, but what we've been using is technically only true for p in the integers. It's been like x to the n, for instance, where n is an integer. Now for this general power rule, we can show that it works for any real number p. So for example, we could take, I don't know, x to the pi, right, and take the derivative of that. Well, okay, use the general power rule, pi x to the pi minus 1. So that's technically new. Let's prove this thing. We're going to use the same fact as before. So here we go. Here's our fact about exponentials. This fact is odd. We can write x to the p as e to the natural log x to the p. Right? E and natural log are inverses, they cancel out, etc. So here's our proof. Okay, proof. The derivative of x to the p is, well, that's simply the derivative of e to the natural log x to the p. Now the properties of logarithms cause this p to come down, so we have d by dx of e to the p natural log x. Now if we consider all this stuff u, we can use the chain rule on this. The derivative of the outside times the derivative of the inside. So the derivative of e to the u is simply e to the u, but it's not u, it's e to the p natural log x times the derivative of the inside, so times the derivative of p natural log x. That's p times 1 over x. Well, now we can bring this p back up to the exponent here and note that all of this first term is still simply x to the p. So we can rewrite this whole thing as p over x times x to the p. Well, x to the p over x simplifies as x to the p minus 1, so we are left with p x to the p minus 1. And we have proven all 6 derivatives, and now we can happily use them in our work moving forward.